Hello everyone, welcome to my channel. I'm Subhrajit Asst, Assistant Professor in Marine Engineering College. Actually, in the last video, while I was discussing about the buckling up spring, the video is stopped due to some technical problem. The same topic in this video I will going to discuss. What is the meaning of buckling up spring? Buckling means bending. And why this bending done? Because of the pre-length. In the last video, I told what is the pre-length, right? Observe here. Suppose this is a shaft or a rod or a bar having diameter D and length suppose L. It is a very short length shaft, you assume. One end is fixed. Sir, if I will take a very short length and diameter D and length is L, then maybe the shaft is stand straight. There is no bending because length is very short. What I will do in the next attempt, same diameter I will keep, but this time 1 minute. Same diameter I will keep. One end will be fixed, but this time the length is suppose 10 times or more than very big length the previous one. Diameter is fixed, diameter not changed, diameter is D suppose, right? Diameter is D, but length is more here. Same diameter D, length is more here. Then what will be happen, sir? Any effect? Can you guess what I told you? What any effect will be produced? Can you guess? Sir, this shaft will be slowly, it will be bent like this. Right? It will bend like this. Have you seen a construction work, building construction work using the column rods? If it is the length is big now, automatically it will be bent. Why it is bent, sir? Because the diameter and length is not in proper ratio. Okay, na? To avoid this kind of bending, I should choose a proper ratio of L and D. Then only the problem can be solved. What is the solution? Solution is, suppose I want to big length, then the diameter also should be big in the proper ratio of the length. Then only the bending will be avoided, right? So conclusion from this discussion is what? If the length is very greater than D, then bending formation will be there. Chance of bending formation will be there. That means we should not neglect the D while considering the length L. The same manner in case of spring also. Okay, na? What will be happen if the suppose the coil diameter fix D, but company manufacture LF is very high length or large length, then what will be happen? If little amount of load will be applied, then spring will be bend like this. It will be bend like this. Why? Because here LF is very greater than D. That means there should be a relation between LF and D so that this buckling effect will be minimized. Buckling effect will be completely disappear. What is the relation, sir? LF should be equal to or less than equal to 4 times diameter of the coil. This diameter of the coil. What the diameter of the coil you are choosing, based on that the free length should be maximum 4 times or less than that, right? Then only this buckling effect will be reduced. This buckling effect will be disappear. Application of load. Otherwise, if if your tree length is not in the proper ratio of the coil diameter capital D, then even if a very less amount of load you are applying, then there is a chance buckling up spring will be formation. To avoid this one, what is the rule? This is the rule. This is the rule, right? This is known as buckling up the spring. Okay, I hope you understood this one. What is the next one, sir? Next one is observe here. If okay, buckling of the bending. For buckling, we have to consider this critical load values K, KB and LF. LF is the pre-length, KB is the stress factor, right? And K is the stiffness of the spring. Later we will see this formula. Okay, just what is buckling I told you here only. Now observe. I told based on the helix angle we can divide the spring into two types. One is, this is called closed coil, this is called open coil, right? So what is the difference between these two? I will tell you in this video. Observe carefully. This is called closed coil and this one is open coil, right? This one is open coil. What is the difference? Difference is, sir, here pitch is zero, almost pitch is zero, but here certain pitch is there. This is one difference, pitch is there, right? What is the next difference? Next difference is, let me move it a little bit below. 1 minute. Suppose I will apply a load here. I'll apply a load here. Apply a load here for tensor. And the load is applied where? At the axis. So it is called axial load, right? Spring is designed to bear the axial loads. So it will apply the axial load here. Sir, whenever the I'll draw one spring coil here. So it looks like this, right? There is no helix angle, or helix angle is less than 10 degree, I told, right? And here the load is applied like this at the center or at the axis. Now suppose the load is P. Now tell me, and this is the spring axis. Okay, this is the spring axis. Now tell me, in this particular picture, for this load, is there any component of force? Is there any component of force? No, there is no component of force. The force is purely vertical. If I'll talk about the horizontal component will come in this directions, and angle is 90 degree, right? Every force having a vertical component, horizontal components. So it is the vertical components which is acting along the axis, and this is the coil axis, spring wear axis, and in this axis the component of P is 0 because cos 90 is 0. One component is P cos theta, another component is P sin theta. But here cos theta means along the horizontal axis, angle is 90 degree, cos 90 is 0. So in the horizontal direction, there is no component of force is 0. And only the force is acting along this vertical directions. So whenever the force is acting along the vertical directions, so in the spring, two type of stress will be developed. This is the cross section of the wear, circular cross section, right? Two types of stress will be developed. One is direct shear stress. Another is shear stress due to torsion, or we can say twisting shear stress. So whenever there is a vertical component of load, that means load in vertical direction, this two types of shear stress will develop in the wear, right? So this is a closed coil spring. Now come to open coil spring. Let me draw this open coil spring one wear. So this is the wear, right? 1 minute. This is the wear. Some angle is there, because the angle is more than 10 degree, then only we can say the open coil spring. And this is the wear axis, right? This is the wear axis, and here the load is applied, and this is the spring axis. This which one? This middle one is the spring axis. Coil axis we can say. And here load is suppose applied like this, vertical load is applied here like this. So I draw separately one coil here. So here also load is applied like this. And this is the axis. Try to understand, very interesting it is. Axis. Right. Now load is suppose P. Tell me, in this diagram, is there one component of force is there or two component of force is there? In this second system, open coil system, I will get two component of force. Okay, na? I will get two component of force. 1 minute. Let me draw once again. This is the load, right? And this is the axis here. Coil axis. This coil axis, this axis, right? Now load is P. What I'm asking, sir? This 4P having single component or double component? Two component. Here in this case only one component because the axis of the wire is pure horizontal, because angle helix angle is zero, almost zero. But here helix angle is more than 10 degree, in this case more than 10 degree. So spring making some coil making some angle. So if coil is making some angle and it is the horizontal axis of the wire, then it will be the vertical axis, right, to the wire. So one axis here, another axis here. Okay, na? So if this angle is helix angle alpha 10 degree, more than 10 degree, 12 degree, then what will happen? You know, the force will be resolved into two component. One is vertical component, another is horizontal component. P sine theta or alpha, P cos alpha. P sine is the vertical component and P cos alpha is the horizontal component. And already in this previous discussion, what we saw for the vertical P, what are the stress developed, sir? Direct shear stress and twisting shear stress. Same thing also here also developed for this vertical component P sine alpha. Direct shear stress will be developed and twisting shear stress will be developed. Okay? Twisting shear stress will be developed because of this vertical component of P sine alpha. Now, since there is the horizontal component P cos alpha is there, then what will be happen, sir? This P cos alpha some effect or not? But in this case, P cos alpha, it is no horizontal component, zero, no effect. But in this case, some horizontal component force is there. That's why some effect has to be there for this horizontal component. You know what is that effect? Because of this force, one more stress will be developed. That stress is bending stress. Okay, bending stress. Bending stress will be developed. So in the closed coil, only two types of stress will be appeared, whereas in the closed coil, three types of stress will be appeared. Direct shear stress, twisting shear stress, bending shear stress also appeared because a two component of force is developing here because of helix angle greater than 10 degree. But in this case, helix angle is very negligible. That's why the angle may be zero, neglected to zero. That's why no horizontal component. So two types of stress will be developed. Right. I hope you understood what is the difference between closed coil and open coil spring. Right. Now coming to the next part. Next part is what I will tell the stress calculations in the spring. Stress calculations in the spring. What is this? Already you have discussed about how the free length we are deriving, calculation of the free length. Now stress calculations. Just I will take a closed coil helical spring. I will neglect the bending effect. Okay, I will neglect the bending effect. I'll take the closed coil helical spring. Suppose, let's observe carefully. Okay, this one suppose I will take Control C. 1 minute. Okay, now here this one only. Okay, this is my stripping. Here I will derive the stress calculations. I will observe carefully. Now, sir, this is what this is called mean diameter, right? Here to here, it is called mean diameter. Already I told mean diameter of the spring. So, right? And here some load is up. This is a closed coil. Helix angle alpha is less than, suppose less than 10 degree. We assume less than 10 degree. And here the load is applied like this, suppose. Right? Like this it is applied. And you know one more important point. Whenever the load is applied to tension a spring, okay, na? For tension of a spring, that time I told you two types of stress will be developed. One is what? Stress due to, or first is two types of shear stress will be developed. One is direct shear stress. Direct shear stress. Another is whenever this load applied, this coil also rotates. This coil also twist with that load applications. Practically, you can observe this effect also. So, because of this, direct stress will be developed. Second one, twisting stress will be developed. Twisting stress will be developed. Here, bending stress will be neglected because helix angle is less than 10 degree. Twisting stress will be developed. Twisting stress means the wire get twist, right? Twist. Okay, when the tension will be there, and this twisting stress developed in which direction? Clockwise direction or anti-clockwise directions. Okay, the whenever the load applied, tension load. This is a tension load. Twisting stress will be developed in clockwise direction. Clockwise direction. And whenever the load is a compression load, that time direct shear stress will be developed. That means load will be applied like this. Okay? Like this load will be applied. So direct shear stress will be developed. Direct shear stress will be developed. Direct shear stress will be developed. Next is twisting also done. But twisting stress will be done in which direction? Anti-clockwise direction. Practically also you can observe the effect. If you have a spring, you press it, you stretch it, you can observe this thing also. Anti-clockwise directions. Okay, na? That means when I'm pressing now, that means I'm trying to press, it will try to, the diameter try to stretch. Length will be reduced means diameter will be try to enlarge. Diameter will be trying to diameter wise it will try to extensions. So diameter extension means it will try to move in this direction, anti-clockwise direction, the spring. But whenever I'm trying to do the tension load, the length wise it will try to increase. In the same way, diameter has to be decreased. Decrease means it should move clockwise directions, right? So same thing, whenever the tension load, direct shear stress, twisting stress in clockwise, direct shear stress, twisting stress anti-clockwise when there is a compression load, right? So this is the things you need to understand, theoretical things you need to understand. Now come to the point. What is the point means? 1 minute. Suppose the load is applied here, you assume this one, tension only. Tension, for tensions. For tensions are, for tensions, two types of stress. First is direct shear stress. Second one is twisting or torsional shear stress, twisting stress. In which direction? clockwise directions, in clockwise direction, right? Now in this diagram, here the coil axis, right? This is the coil axis, and the cross section of this wire is circular. Here, here circular. Here also circular, circular cross section. Right. What I will do, I will take this cross section here, circular cross section, and this is the axis, and here load is applied. Observe carefully, very interesting. Load is applied, and this load will be transmit to everywhere. Here. Same amount of load it should be assumed. It will transfer everywhere. That means this load also transfer to this circular cross section also. That means here also F. If the load will be transferred here to this circular cross sections, okay, this is inner side. This is the inner side, right? This one is the inner side, and this is the outer side. And the same load will be transferred everywhere. This is called direct shear stress. So here is the load transfer. Here is the load transfer. What is the load value, sir? Let it is F. Okay. So F will be transferred here also, here also. Everywhere. I am taken two extreme edge, inner edge and outer edge. This is inner edge and this is outer edge. So inner edge F, outer edge F. This is direct shear stress. Now stress because of twisting. Which directions are shear stress? Shear stress because of twisting. Clockwise direction. Clockwise direction means here, in this direction, here, and here. Right? Clockwise directions. Okay, na? So if I'll find out the resultant stress because of this two stress, which stress, sir? Resultant stress. Now tell me, which side, inner side or outer side, will experience more stress, sir? Obviously inner side. Why? Because you see, this is the twisting stress direction and this is the direct stress direction. Both are same. That means both will be odd. But in this case, direct stress direction is this one, and twisting stress direction is this one. Here minus will be happen, negative will happen. So which side experience more resultant stress because of direct stress and twisting stress? Always inner side. Always inner side. Same thing also we can, you can find in case of compression spring also. Observe, that means when the load is applied, downward direction. So this is the cross section, right? This is the cross section. This cross sections, and this is the axis. Suppose this is the axis again, and this time the load is applied. Load is applied, not tension. Load is applied, compression load, right? On the spring, compression load is applied. Suppose like this, right? So compression load means it will be compressed. I told. Again, two types of stress will be developed. First is direct shear stress, second is twisting stress. So direct shear stress means this load will be transmit everywhere, here, every cross section of the where the same load will be transmit. So here is the F, here is the F, right? Next, since it is compression, I told the twisting will be done in anti-clockwise direction, not in clockwise direction. Anti-clockwise direction means in this direction, in this direction. Shear stress, every surface will be, the circular section, shear stress will be developed throughout the circumference, So I'm marking the shear stress here, right? Now tell me, this is inner edge. Okay, this is the inner edge and this is the outer edge. Which edge will be experienced more resultant stress, sir? Obviously observe here, this is twisting and direct direction same. Here it will be odd, but here direction opposite, na? Here it will be negative. That means the more resultant stress will be experienced in which side? In the inner side. Resultant stress will be experienced in the inner side, right? And one more thing I will tell. And because of this direct stress, I told direct shear stress, every part of the spring will be experience the same amount of load, that is F. Here also, here also, here also, here also, everywhere F, everywhere F, right? If I'll draw the shear, direct shear load in the diagrams, observe carefully how it is looks like. Simple. This is the cross section of the spring, and this is the center axis. Okay, na? Center axis. Okay, 1 minute. Center axis. Then the load will be direct, due to direct shear load, everywhere same load. Suppose it is tension, then here also, here also, here also, same height. Why? Because everywhere F value is same, from inner edge to outer edge, any edge you will take direct shear stress values. Now, what about the twisting stress? If it is a wear, shear stress developed fiber to fiber. This wear is made here one fiber, here one fiber, here one fiber. Again, middle axis will come, right? Then one fiber, then one fiber. Like this, layer wise, this wear is made. Spring wear is made layer wise, and shear stress always maximum at the top fiber, top layer, and shear stress values reduces towards the center. The shear stress value becomes 0. Okay, have you seen in the fluid mechanics, viscosity is there, right? Viscosity, water is there, water flowing. The water viscosity is more at the top layer, and if you go down, the viscosity becomes 0. That's why viscosity curve is like this. Why? Because here it is more shear stress will be experienced, and below the layer less shear stress, below the layer less shear stress, below the layer less shear stress, and the bottom layer shear stress becomes 0. In the same way, if it is a wear and twisting is done, then because of this twisting, more shear stress will be developed at the extreme fiber, here also. And if you go towards the center, the shear stress will be gradually reduces, and at the center the shear stress become 0. If I'll show this twisting in the diagram, then how it is looks like, observe carefully. Let it is the cross section, is the cross sections, and this is the center, right? And here what will be happen, I told at the center point the shear stress value is 0. So here it is more extreme fiber, it is more, then reduces, here become 0. Again increased, and at the extreme fiber again it become more, right? Okay, na? It is which direction, sir? See, shear stress, na? Twisting means it is in anti-clockwise direction. That is a compression, for the compression, right? Okay, na? Compression, anti-clockwise directions, shear stress. Now the resultant stress, I told, resultant stress, that means combination of direct stress and combination of this twisting stress. In which edge the resultant stress is more? I told in the inner edge resultant stress is more, in the outer edge resultant stress is less. Because here observe carefully, in inner edge, in tension also, in compression also, just I erase, it will be odd, but this side it will be minus. Okay, na? That's why in the inner edge the resultant stress is what? More. Okay, observe carefully. I'll draw that resultant diagram also, observe. Let it is the circular cross section, right? And here this is the center axis, this is inner edge, suppose inner, and this is outer. Okay, outer. Then what will be happen, the inner edge will be, if it is suppose compression means This load line will be below, come down, right? I have done tension here, down like this, down, 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 because this is compression, right? Anticlockwise. So here inner edge stress will be more. This is inner edge stress will be more, and outer edge stress will be less. Small line, small height, small height, small height, small height. Right? If we draw the diagram, it will looks like this. So inner edge subjected to more shear stress comparison to outer edge. Why? Because of this explanations I told, right? Okay. Now let us try to derive the formula. How to derive the formula? Sir, I told two types of shear stress. One is a direct shear stress, another is twisting shear stress. Shear stress due to twisting. For direct shear stress, formula is what? Suppose like direct shear stress. Suppose tau 1, load is P, cross sectional area of the wire, P by pi by 4 into d square, or we can write 4p by pi d square, right? 4p by pi d square, because cross section is circular and diameter is small d. Okay. Now this is the direct shear stress. Now shear stress due to twisting, suppose T2, I have to find out. How to find out? I will find out from the torsion equation. Torsion equation is T by J tau by R C theta by EL. I hope you know this equations, torsion equations, right? I will take this 2 for derivation of this term. Here tau 2, because twisting, tau 2 I have taken here. Now T is what? Torque. T is torque, and T is torque is what? P into radius, coil radius. This is coil. Coil diameter is D. Wire diameter is 1 minute. Wire diameter is small d, but coil diameter is capital D. And here load is applied. Load into this radius is called perpendicular distance. It is called torque. P into R, or here we can write P into D by 2. Torque. What is J, sir? J is polar moment of inertia. Polar moment of inertia means moment of inertia about the orthogonal axis. Orthogonal axis. You know, there are three axes: x-axis, y-axis, and the z-axis. Right? So the moment of inertia about the z-axis is called polar moment of inertia. And IZZ perpendicular axis theorem you have to apply. IXX plus IYY. And you know, for the circular section, the moment of inertia about the x-axis is pi by 64 into d4, and along the y-axis also same. And IZZ become pi by 64 d4 plus pi by 64 d4. That means 2 into, so 2 it will be cancelled by 64, 32. So J become, or IZZ or J become pi by 32 into d4, the polar moment of inertia. And R is what? Small r, this radius R is d by 2 also I can write. Now I'll put every this mathematical expression in these equations, right? What is it, T, sir? T is P into d by 2 divided by J is pi by 32 into d4. Okay, and tau 2 I have to find, and R is d by 2. Okay, P into d by 2, this is d to the power 4, small d, right? Small d. Okay, now 4 d cancel, it will become q, and it is 216, right? 216. If I will simplify this one, what I will get, and here again 2 it will cut by 8, right? If I will simplify this one, it will come this 8p, okay na, 8p into d divided by pi is there into dq equal to tau 2 is there. right? Tau 2 is there. Right? This is the stress I calculated because of twisting, and this is the stress I calculated because of direct shear stress. Now, what is the resultant shear stress? Resultant shear stress is tau 1 plus tau 2. It is denoted by this symbol tau equal to tau 1 plus tau 2. So 4p pi d square plus 8pd pi dq. Okay, na? What I will do, sir, I will take common 8p d, I will take common divided by pi dq. I took common. Then what I will get? This is become small d divided by 8 na 18 2 4 2 and d 2d here plus 1. Okay, plus 1, right? So this term d by 2d plus 1, it is called as a shear stress factor. This is called shear stress factor. This term, it is denoted by the symbol Ks, shear stress factor. If I'll replace this expression to Ks, then finally I will get the tau value. Tau value is 8pdks divided by it's q, right? Pi dq and pi dq. This is the expression. Resultant shear stress for the compression spring or tension spring. We can find out like this, right? It will simplify further, because we know the relation between d and small d. D by d is called, this d by d is called c, spring rate. It is called spring rate. D by d is called spring rate. Okay, na? Spring index, not spring rate. It is called spring index. Spring rate is deflection, delta. Symbol is delta. It is called spring index, d by d. So if I'll replace this one d by d, then I will get here tau equal to 8p ks by pi d square, here d by d. So dq, I wrote d square d. So d by d is equal to what? C, na? So in place of this one, I will write c. Right? So then 8p ks c by pi d square is my one more expression of the time tau. Here also we can d by d is there, na? In the sometimes in the question spring index value is given. So how to find out ks? Here also we can do d by d is 1 by c. So 1 plus 1 by 2c. It will become 1 plus 1 plus 1 by 2c. This k is equal to, right? In the form of spring index also you can have. So this is the formula for shear stress in the spring. But in this formula, we have not considered the curvature effect. Curvature effect of the spring. This is without curvature effect. We will consider the curvature effect. Then we have to consider one more stress due to curvature. That means spring are curved, right? Like this circular section here, curve is there. So because of this curve also, some stress will be developed, because of this curve. But in this formula, we have not considered that curvature effect. Only we consider two stress. One is a direct shear stress, another is twisting shear stress. In the next video, I will discuss about the remaining this advanced level topic by considering this curvatures and deflections. All these things we will discuss. And it's a good point to stop here. So till then, take care and bye.